Okay, so welcome to a new season of the Oxford Discrete Maths and Probability Seminar. It's a great pleasure to be starting off this term with Guillem, who's going to talk on maximum stationary values in directed random graphs. Thanks.
So yeah, thank you all, Alex. Thank you, Alex and Christina, for the invitation. It's really nice to be here, even though it's online. But anyway, it's always nice to talk at your seminar. So I'm gonna be talking about random walks on directed random graphs, and I'll mostly focus on the values of the stationary distribution, and in particular from the values of the stationary distribution. I'm going to be also focusing on the extremal values, and in this particular case, I'm going to be looking at the maximum values of the stationary distribution. So let me just say that this is a joint work with Xing Shi Cai, with Pietro Caputo, and with Matteo Quattropani. If you have any questions, you can ask in the chat. I think I'll see it, or you can, just feel free to unmute yourself and stop me at any time. So let me start by presenting the model that we're going to work in, and this is called the directed configuration model. So maybe some of you are familiar already with the configuration model or the pairing model. So this is just the directed analog of it. So you're going to have n vertices, and then instead of do you see that, right? Yeah. So instead of having degree sequence, a normal degree sequence, you're going to have what is called a bi-degree sequence, and a bi-degree sequence is just a sequence of pairs, d1 minus, d1 plus, so and so on, dn minus, dn plus, which are going to mark the number of heads and the number of tails that a particular vertex will have. And the only condition that we require is that the number of heads and the number of tails should be the same, and this is what we will call m. So for m, for me, during all the talk, m is going to be the number of edges. So what's a directed configuration model? So the only thing I'm going to do is I'm going to take, well, the same thing I'm doing in the configuration model when I'm taking a uniform pairing, but in this case, I will insist that the pairing is a uniform random pairing between the heads and the tails. So I'll do a uniform matching of the heads and tails, and this will induce a graph, a directed graph. And in fact, it's not necessarily always a graph, but it's, in fact, I have loops and I can also have multiple edges. So in fact, it's a multi-graph. And let me say that if you really want your graph to be simple, so not to have any loop or multiple edges, all the things I'm going to say today, they also transfer to this setting where your graph is simple. Here I just put a picture of how this looks like for a particular choice of degrees, but for you to have an idea of which kind of object we are looking at. So this is going to be our model. We have this random object, and we want to perform random walks on this random object. So let me just introduce a couple of basic things about random walks. So now let's think about random walks on a given digraph. So this is just, I have a given digraph, and I'm defining my random walk I want to study is going to be the following. So it's just the probability that I move from a particular vertex u, from u to v, this doesn't depend on the time t, and it's just the number of arcs that go from u to v divided by the total number of arcs that go out from u. So in words, this means just at the particular time, I'm at a particular vertex, I have du plus edges going out from me, and I just take one of them uniformly at random, and I move to the target. Okay, so I'll need a couple of definitions. So the first one is well known, is a stationary distribution. Stationary distribution is a probability distribution that satisfies this equation here, where p. Just a second. Okay. It has a bit of lag, sorry. Well, P is just this matrix. It's called the transition matrix. It's a matrix that has these entries here. This is the probability of going from U to V. So this is going to be a stationary distribution. And let me recall, what does it mean, a strongly connected component in the digraph? This is just a maximal subgraph H. So just for any pair of vertices, I have a directed path that goes from U to V, and another directed path that goes from V to U. So the ergodic theorem for Markov chains in this setting says the following. So if you have that your digraph has a unique, so your digraph can be partitioned into strongly connected components, and if it turns out the case that there's only one that is attractive, and by attractive here I mean a strongly connected component is attractive if there are no edges going out from it. So if somehow all the strongly connected components are connected in such a way that there's a unique one that cannot be left, then your stationary distribution is also going to be unique. and it's going to be supported in your strongly connected component. And moreover, like for any pair of vertices, so this, you can see this as the average amount of time that you will spend at a particular vertex in your random walk. So then this average amount of time that you will spend at a particular vertex will converge to the stationary distribution of this vertex, regardless of the starting point. So no matter the starting point, in the limit, the fraction of time that you spend at a particular vertex is pi of b. So in this sense, you can see this, in this case where pi is unique, you can understand this pi as a measure of popularity in your graph, right? So it's the time that you spend in this vertex. So vertices with large pi are very popular vertices, like popular vertices, and vertices with a small pi are vertices that are not so popular. And somehow this will be interesting later when I'm talking about, when I'm using this stationary distribution to rank rank the elements of the network. Okay, so let's mix the two things. So we have the random walks and the random configuration model, directed configuration model. I'm going to do random walks on this directed configuration model. So just let me clear that there's two levels of randomness. So, and it's like the proofs are not going to be like this, but for us to understand it, it's the best thing to do is just you imagine as first sampling some random graph, some GDN, some instance of this configuration model. And once you have this thing, you perform your random walk on top of it. And then it's not very difficult to prove this small lemma, that if your maximum, sorry, not maximum, but minimum, if your minimum out degree is at least 2, then with high probability, it will be the case that there is only one strongly connected component that is attractive. So in particular, we will have this unicity of pi, and this will be something that we will really like in this situation. So let me give you like a very, very rough idea why this is true. So imagine that you have a vertex y, and so you don't know anything about its in degree. So it could be 0. If it's 0, of course it's not going to be in the strongly connected component. It could be positive. So maybe you have some sort of in neighborhood, but maybe after some time this neighborhood dies out and there's nothing else here. But what's going to happen is that if you manage to have this in neighborhood for a while and become a big, so at some point this is a big in some sense. So this are the in neighborhoods. Then because of the out neighborhood at least 2, for any vertex x, you're going to have out expansion. So you're going to out expand, and at some point you will have an edge connecting this out neighborhood of x with the in neighborhood of y, and this means that you will be able to go from x to y. And since you will be able to do this for every x, then this y will belong to the strongly connected component. So so this minimum degree at least 2 is essentially also necessary. Why is so? Because if you have minimum degree 1 or even 0, let's think about the case of having vertices of degree 0. Then if you go to a vertex that has out degree 0, then somehow maybe you can reach this vertex, but you cannot continue. So somehow the stationary distribution will be supported only on this vertex, and this is not very interesting. So it's kind of a normal assumption. So these are going to be the assumptions I'm going to take for my degree sequence. So it's kind of natural to think about the minimum out degree being at least 2 in order to make the problem interesting. Otherwise, it's rather trivial. And we're going to also take a couple of more conditions. So we're going to take that the maximum degree is going to be bounded in n. So and this is essentially because this will help us. This is somehow needed. This is somehow it will make things easier from the technical point of view. So this means that, so this is regarding the out degrees. So the out degrees are going to be at least 2 at most constant. And the in degrees, we're going to be more generous. So we're going to allow much more variety of degrees. The only thing that we want is that the so-called 2 plus eta moment is linear, where eta is something that is positive. So as small as you want, but so we want a bit more than the second moment to be finite here. And this is the only condition that we're going to have on the in degrees. So I'm going to assume all these 3 conditions during the talk, and in my results I will not explicitly say assuming that we have these three conditions, but all the things I'm going to say, I'm going to assume these three conditions. So, so let me go to the stationary distribution of this directed configuration model. And let me start by just noting that if you look at a random walk in the undirected graph, then knowing the stationary distribution is kind of very simple. And a stationary distribution is always given by the degree of vertex divided by m. So maybe the graph is random, maybe the graph is deterministic, maybe the graph is as bad as you want, or as good as you want. Your stationary distribution is always going to be given by that. And this will be unique in particular if your graph is connected. So even if you have a random graph, you have a deterministic stationary distribution. So this is not the case in the directed setting. In this case, pi, this stationary distribution, is going to be a random measure. And it will strongly depend on not only on the degrees, but really on the whole geometry of the graph. So small changes in my directed configuration model will affect the stationary distribution of the whole graph, in fact. As I was saying before, you can see pi as a measure of popularity, meaning that it's the fraction of time that you spend at that vertex on a random walk in the long range. So maybe it's tempting to think that the stationary distribution should be related somehow with the number of edges that you have. What do I mean by that? So if someone has a lot of vertices pointing at him or at her, this means that this person probably is going to be popular. So this means that pi should also be large. So maybe, so if you look at, if we say that mu in is the in degree distribution, and by in degree distribution, I mean just the in degree divided by m to make it a probability distribution, maybe some guess is that there should be mu in maybe is similar in some sense to pi. Let me tell you that in general, this is very far from being true, because I can have, let's say, a couple of examples where this is not going to happen. For example, I could have a vertex with a very large in degree, but then for some reason, maybe these vertices have in degree 0 for all these ones here, meaning that they do not belong to a strongly connected component, so they have a stationary distribution 0. So in particular, this one here will also have a stationary distribution 0. Pi of, let's call it W, is also going to be 0. So maybe you can have a very large in degree, but still have a very small stationary distribution. Maybe you're not even the strongly connected component. And in the other direction, maybe there's a vertex that for some reason he's very popular, and also like he's connected to vertices that are also very popular for some reason. So meaning that this pi is pi of W is large, but maybe this vertex only has one out degree and connects to a vertex, let's call it Z, that has only in degree 1. But this one, for some reason, is getting all the mass that this W had. So pi of Z is also going to be large. So in a I'm not saying that this is going to happen for a random graph, but in a deterministic setting, somehow you could graph some examples with very large in degree but very small pi, or examples with very large, very small in degree but very large pi. So it's also not clear why these two things maybe are similar. So let me before going, as I said, I'm interested in extremal stationary values, but let me talk a bit about the typical ones before talking about the extremal stationary values. So I'm going to be interested in this empirical distribution, which is simply what I'm going to put here. I'm going to put a Dirac distribution, Dirac mass at, instead of putting the Dirac mass at pi of b, I scale it by m. So I just put the Dirac mass at m times pi of b. And I just put the mass 1 over n. So in fact, this is the distribution, or the density, of pi of b, where phi is chosen uniformly at random among all the vertices. So I'm interested on the value of pi for a randomly chosen vertex. And then there's this result of Bordelais, Caputo, and Sales, Here I also put our names because we generalize this for a more general degree sequence, but we're just following their proof, so it's really their result. And it says the following: it says that there exists some sequence of deterministic laws that I call Ln, such that with high probability, when you look at a particular distance, which is called this one Wasserstein distance, between the empirical distribution for the stationary values and this deterministic law, then this distance goes to 0 as n goes to infinity. So I'm not going to go into details about what is L of n or what is this one Wasserstein distance, but just let me say that this result captures the typical values of pi. So it tells you the typical values of pi, say, I don't know, 99% of the mass, is going to behave like this Ln behaves. And in particular, it also tells you that it's not going to be too different from muing. So one of the intermediate results that we need, that they need, and we also need to prove this statement, is that if you start with the distribution muing and then you walk for edge steps, so this is this distribution that you get if you start at muing and you walk for edge steps, then you converge to the stationary distribution in relatively few steps. In fact, this thing can be improved to constant, essentially. But I didn't put it here because we don't prove this. So Bordenave, Caputo, and Sales, they prove that it's enough to walk constantly many steps starting at the in-degree distribution. In our case, we only prove this weaker statement. So with this slide, I wanted to give you the idea that we understand how typical stationary values behave. They are somehow related to this muing. But as I said, like we are interested in looking at the extremal values. So what do I mean by extremal values? So we're going to be interested in two objects. The first object is what we call the maximum stationary value, pi max, which is just, as I said, like the maximum values of a stationary distribution. And more in general, we're only not going to be interested in the maximal one, but also on the upper tail. So say that I give you some I don't know, some points A, n to the A. I want to know how much mass do I have in my empirical distribution that is larger than n to the A. So I'm going to be interested in these two elements. So I'm going to talk for the next.
Sorry, Guillem. In the previous slide, what does the Ln depend on?
It depends on the degree distribution.
Okay.
So it really depends on the degree distribution, and it can be defined as the law of some random variable that depends on some stochastic fixed point equation. So defining everything now properly is
I just wanted to clarify that it depends on the degree distribution.
Yeah, it depends on the distribution. Thank you, Agnes. So as I was saying, we're going to be interested in these two objects. I'm going to first talk about this pi max, and then I'm going to move to the upper tail. And apart from understanding these extremal statistics of the stationary distribution, one of our motivation was to pi is used sometimes to, as I said, as a measure of popularity. So you can obtain a ranking of the elements of your graph by ordering them by decreasing pi, value of pi. And this is very close to what the PageRank does. And then at the end of my talk, I'll try to say how our results apply to PageRank. So I'll try to say something about PageRank. Let me also say that if for some reason you say, well, I'm interested in the extremal stationary values, but not the maximal ones, but the minimum ones. By minimum, I mean the minimum one that is positive, right? Because they're going to be stationary values that are going to be 0 if you are outside the strongly connected component. But the minimum positive ones is something that, and the behavior of the lower tail is something that it has also been studied, and it has been studied by Pietro, Caputo, and Matteo Quattropani, who are also co-authors of this work, and by myself and Sai. So we started looking at the minimum stationary values, and then we decided to join forces to look at the maximal ones. But if anyone is interested, I think it's also a very interesting problem. This is like the less popular, but still a bit popular vertex in your directed configuration model, and you can look at these two papers. So okay, so let's talk about pi max. So Pietro and Matteo already looked at pi max in their paper, But they were restricting to a case where you have bounded degrees. So we also have bounded out degree, but we want to allow like more general in degree distribution. But in their case, they were really looking at maximum in degree that is constant, that doesn't depend on n. And what they prove is the following. So if you have such a condition here, then with high probability, your pi max, once you scale it by m, it's going to be at most logarithmic. So this means somehow that you have a logarithmic fluctuation from what you're expecting. And the exponent of this logarithm is something that they also give explicitly and depends on the minimum out degree and the maximum in degree. So I'll try to give you some intuition why these two parameters pop up here when you're looking at the most popular guy. So again, we're looking at pi max. Pi max is the most popular guy, so the guy that is easier to access. And if you want a vertex, I mean, this is a bit of a heuristic, but if you want a vertex to be very popular, you like that this vertex satisfies two things. So the first one is that it has many paths leading to it. There's many paths that go to it. And the second thing, which is also very important, is that these paths are easy to follow, right? Because you may have lots of paths, but if these paths have a lot of branching, then you're not going to be so popular. So there's a combination of two factors: having many paths leading to this vertex, and this path also being easy to follow. And the easiest it can get is if you always have a profile that is of the form delta minus small delta plus. So this is somehow the profile of the vertices in your neighborhood that will make you more popular. And if this is the case, then is when you get the pi max. And as I was saying, like this pi max is going to have some logarithmic deviation with respect to the maximum in degree, right? Because the maximum in degree is just delta minus divided by m. But delta minus was a constant, so it's of order 1 over n. So it deviates just a logarithmic factor, at most a logarithmic factor with respect to this in degree distribution. And also, let me say that this upper bound is also like, they can also obtain lower bounds. In particular cases, essentially like if you have linearly many vertices with these degrees, with these extremal degrees, then they can show that there exist some vertices that are that popular because of that reason. I mean, somehow it's not so unlikely to get these neighborhoods where everyone is really with the right profile to make you popular, and you can really get this deviation. So for the bounded case, somehow this is the answer. And what we would like to understand is what happens in the unbounded case, the case where you allow delta minus to grow. And this is our first main result, which is the following. It's quite simple. It says that the maximum stationary value, like scaled by m, this is more or less delta minus. And in which sense? So it's at least always delta minus times something that tends to 1. So the lower bound is quite strong, I would say. And for the upper bound, we prove that it can deviate at most a log n from delta minus. So these are the two bounds. And these two bounds are tight. So we have degree sequences where each one is attained. So for this one here, this is essentially repeating the example I said before. So with these examples that Pietro and Matteo had, you can construct degree sequences that will give you pi max multiplied by m to be of delta minus times something that is almost a log n. So log n to the 1 minus epsilon or something like this. So there's no much space for the upper bound to improve. And in the lower bound, it's still stronger. In which sense? So we also prove something that is, I like this result somehow. I mean, it's an example of the tightness, but it's also a result itself. And it says the following. So you have a degree sequence where your maximum in degree is outstanding. And now I'll say what does it mean to be outstanding. Then pi max is precisely the maximum of the in degree distribution times a small multiplicative factor that goes to 1 and then goes to infinity. So what do I mean by outstanding? Outstanding, so there should exist, what does it mean to have a maximum degree that is outstanding? So there should exist this W that's going to be the one attaining the maximum degree in degree. And then for every Z different than W, I should have that dz minus is a little o of dw minus divided by log n. So this means that if there's a bit more than a logarithmic gap between your maximum degree and the second one cannot somehow overpass the maximum in degree, and this pi max is going to be just the maximum of the in degree distribution. And it's also easy to see somehow that there's only going to be one vertex that will attain this pi max, which is precisely this W. That's the one that has the maximum in degree. So I think, so this gives a quite general family of sequences that satisfy equality for the lower bound. Okay, so just summarizing a bit, we have this upper and lower bound for the pi max. Both are tight. And I'll try to explain you a bit how you get, I mean, the proof for the lower and the upper bound are quite different. The proof of the lower bound is relying more on the previous papers that existed on the topic and on the machinery that Bordenave, Caputo, and Sales developed to study the mixing time in this model. So I'm not going to go into this because I would need a bit too much to introduce too many things. But I would talk a bit about the upper bound, because the upper bound somehow the proof is more self-contained. So I will try to give some ideas for the proof, and because I don't want to, I mean, I cannot spend too much time into this. Let me say that I'm just going to prove that pi max is at most this thing, where here instead of a 1, in general I would like to prove a 1 here, I'll put a 7. And then you can do improvements and really turn the 7 into 1. But hopefully the idea of the proof is the same. So the first thing I'm going to do is instead of looking for pi, I'm going to look for a new distribution, new proxy distribution. And this distribution is going to be this mu t of y. So mu t of y is just the probability that my random walk is at y if I started at the place that is uniformly random. So I start at the place that is uniformly random. I can also write this as 1 over n sum p t x y for all x. So I start at each vertex with probability 1 over n, and then I walk for t steps, and I ask for the probability that I'm at 1. So this is my new distribution. And it turns out that if you want to bound pi max, it's enough to bound this new distribution. And the reason, for a large t. So I'm going to take t in this case to be log cube of n. And using the results that we already know, it's not too hard to prove that the total variation distance between a stationary distribution and this new distribution is going to be small for t being log cube of n. The reason why this is true is because the mixing time of this model, I'm not going to give more details about this, but the mixing time is of order log n. So if I walk for log cube of n, this is log square time the mixing time. So the total variation distance to stationary decreases exponentially on the number of extra steps that you walk after the mixing time. So in this case, you're going to get some bound of the form, even e to the some constant log square of n, something like this. But just let me say that if you take t to be log cube of n, then these two distributions have a small total variation distance, so it's enough to study the new one. And when I'm going to prove for the new one, I'm going to take k is going to be the number of k is going to be in this case just some logarithmic amount. I want to look at the kth moment of mu ty. So here I'm fixing y, and my expectation is over the environment. I'm going to prove that this kth moment of this distribution is of this form. It can be bounded by something of this form, where here I have k, which is this k here. I have my t, which was this log cube, and I have also the in degree, and I have my m. And you can see that this really looks like this, right? Because I have this t squared that is going to be a log to the 6, and I have this k that is going to be a log n. So after that, I will be able to apply Markov inequality and somehow compute if I manage to prove something like this. And the idea to prove something like this is the following. So we're gonna compute this expectation using something that is called the nil random walk construction. And the idea is that we're gonna start independent random walks. We're gonna start k of them, k independent random walks, starting at also independent and uniformly at random distributed vertices. But that is important. These random walks are gonna be run on the same environment. So we start with, like, at the beginning, there's nothing revealed. And then we start at a random vertex, and we start going, like we start walking randomly, and at the same time we walk randomly, we construct our environment. And at the beginning, we'll have fresh randomness. But then for the second walk, we have already one walk that has exposed part of the environment. And then we'll have to deal with the second walk, knowing that the previous one has already revealed part of the environment, and so on. And computing the kth moment of this mu-t of y is the same as computing the probability that these k walks will be, after t steps, precisely all of them at y. And why can you bound these by something like this? I give you like very rough idea. So imagine that at some particular moment you have your y here, and maybe you have constructed some, I don't know, maybe started with this your x1, and maybe you started with the x2, which didn't have anything to do with x1. Maybe x3, then at some point was joining here, and then was going for a bit here, then maybe it was jumping here, and was going for a while in this direction, and then maybe it was kind of going like this, right? So at a particular moment, you have exposed part of your environment, and now you start with a new random walk. Let's call it I don't know, for example, I don't know, XL, and you want to know somehow which is the probability that finally you will end up at y. You want to bound this. You want to say that it's not too large. And the idea here is that as long as you don't touch the part that is already unveiled, and like that has been revealed, then you have fresh randomness and things work well. And what's the probability that somehow you touch, and at the moment you touch to the old trajectories, at this moment maybe you don't really know what's going to happen. And maybe without knowing, you'll end up at y with probability 1, something like this. So what's going to happen? So the probability that you eventually attach to this part that you have already revealed is at most the following. So you have these steps where you can attach to this previous thing that has been revealed. And how many vertices do you have? You have at most t times k, because you have run k at most k walks of length t. And each one has in degree delta minus. So this is this is the number of steps that you have to attach to this old revealed part. This is the number of half edges that somehow make you enter this already revealed part. And the number of edges in total is m, minus maybe something that you have already matched, which is not very important. So at the end, this is less or equal than 2 times k t squared delta minus divided by m, which is the thing that you wanted to prove, right? So for each walk, the probability that eventually will be at y times t is at most this amount. So once you have this bound on the kth moment of mu-t to the y, then it's easy because you can just use Markov. So you use Markov with the kth moment, and because k is log n, and because you have set your constants correctly, what you get is that the probability that this thing is large is very small. It's small enough so you can hit it with a union bound. So you know that for any vertex, so with high probability for all the vertices is going to be at most this pi star over 2, and then you can use 1, which was telling you that in fact pi and mu-t are very similar, to conclude that the maximum of the stationary distribution is at most this thing. So hopefully I managed to give a bit of idea how you prove such a statement. As I said, this 7 can be turned into 1 by being more careful on how you can access this thing that has already been revealed. So let me move to the upper tail. As I said, I'm going to talk about Timex, but also about the upper tail, and I'll try to be go a bit quicker at this part. So I like to so for the upper tail, we would like to study something that is called the power law hypothesis. And for this, first I need to tell you what that does it mean for me that something is power law. So there's many definitions of power law. There's some that are more strict and some that are more relaxed, more weak. So in my case, I'm gonna take a pretty weak definition, a pretty ample definition of being power law, and I will say that an empirical distribution has power law behavior with a given index kappa. If for every a in this interval, I have that the that the mass of the upper tail, of this upper tail here, is of order n to the minus a kappa, plus minus some epsilon, so plus minus little of 1, say. So as I say, like, this is somehow very generous, so I give you a lot of room here. So in this sense, I'm taking a lot of empirical distributions that I accept as being power law. And I want to understand the relation between what does it mean for the in degrees to be power law and for the stationary distribution to be power law. So I'm going to take the empirical distribution of the in degrees, which is simply this thing here, just the fraction of vertices that have in degree at least n to the a. And at the same time, I'm going to be looking also at the thing that I have already defined before, which is empirical distribution, the tail of the empirical distribution for the stationary values, which is the mass of vertices that have stationary measure at least n to the a divided by m. And I want to compare these two things. And the power law hypothesis, which is something that in fact normally is referred to in this PageRank setting, but you can also state it for the random walk setting, is that in general, if you have a power law in degrees with a given index, then this should imply also power law behavior for the stationary distribution with the same index. And that's some hypothesis. What does it mean to be an hypothesis? It's just something that has been observed in reality, so in real world networks, and it has been studied. It was studied by the physicists like in the early 2000s, and later, like in these last years, it has been also given some mathematical framework, and there are several results in this direction, and somehow our results in this paper also support this power law hypothesis in some sense. So let me say first, okay, so if you think about the results I gave for this one-Wasserstein convergence of the empirical distribution, plus some properties of this deterministic law that I haven't talked about, then this tells you that in fact, if you let your n go to infinity and you look at the limiting distribution of this empirical measure, then you'll be able to see that this limiting distribution also has a power law tail with the right exponent. And this is something that is not new. I mean, it's new in this context of random walks, but this is something that has been observed in the PageRank setting by quite a lot of people. Here I have some references about it. But what we really prove, well, I mean, maybe the main contribution of this paper in terms of this power law hypothesis is that somehow we can prove this power law hypothesis in the sense that I gave before. So without having to make n go to infinity. So what do I mean by that? So what we prove is that if your in degrees are power law distributed with index kappa, and here kappa has to be strictly larger than 2, and this is related to this 2 plus eta moment that I was talking before, then with high probability, your stationary values will also be will have power law behavior with index kappa. So this is saying, I mean, the first statement somehow, this statement at the top, is telling you about, this statement at the top is telling you about the power law behavior of the tail, of the upper tail of a random vertex. And somehow this is saying, well, I mean, you don't need to go to the limit. You can really go look at the particular n, and the extremal behavior, the upper tail of this will also behave, and the stationary values will also behave like a power law distribution. Let me say that in particular, we can also prove, I mean, the upper bound for behaving like a power law is something that also holds for any sequence that has a kappa bounded moment. So in some sense, our result, what is proving is that among all the sequences that have kappa bounded moment, the one that maximizes the upper tail is the power law distribution, which maybe, I don't know, maybe there's some intuition about it. I'm not sure I have it, but how is saying that if you really want to maximize, I give you, I mean, I tell you that you should have a bounded kappa moment, then the distribution that you should choose for the in degrees, if you want to maximize the stationary distribution, is the power law. Finally, let me say something about the PageRank, as I promised before. So the PageRank random walk is a modification of the random walk I told you. So here we're going to have a parameter alpha. This alpha is the probability, sometimes it's called the the teleporting probability is the probability that we just decide that we're going to stop the random walk that we were doing and restart at a new vertex. And lambda is the teleporting distribution. So at the moment we get tired of doing the random walk, we're going to jump, and we're going to jump with probability alpha, and we're going to land to places with probability lambda of v. We're going to land to v with probability lambda of v. So here I just put the expression. So with probability 1 minus alpha, you do the same that you used to do before. You just follow your random walk. And with probability alpha, you just move to a random place according to this distribution lambda. And this power law hypothesis, as I said before, comes from the PageRank random walk, because this is what people are interested in. As I said, like, there's a lot of empirical observations that suggest that this should be the case. And also there's been some mathematical evidence in the last years. And here we just prove the same that we did for the random walk, but for the PageRank walk, meaning that if the alpha ends are bounded away from 1, and lambda of n is almost uniform, so it cannot deviate too much from the uniform distribution, then having power law in degree distribution with some index kappa at least 2 implies that the stationary distribution is also power law distributed with the same index. So in some sense, this establishes the power law hypothesis under this notion of being power. So let me finish with just a recap of the results I gave, and also with some open problems. So just let me remind you about the conditions we had. So we wanted our out degrees to be between 2 and constant. So they are all constant, at least 2. And also we had this third condition that was bounding the 2 plus eta moment of the indegrees. And what we prove is that under these conditions, you have that your pi max multiplied by m is essentially the maximum degree with a bit of fluctuations, both fluctuations being tight. And the second result, that's the one I was giving for the upper tail, is this sort of power law hypothesis holding both for the random walk, but also for the PageRank random walk, that says that if your indegrees are power law, so is your stationary distribution. And there's like plenty of open problems that we don't know how to do at the moment. I'm going to give a couple of them in case anyone is interested. So the first one is under which additional conditions you can close the gap that you had in A, right? So we know that in general, you cannot close this gap. I mean, there's tight examples inside, but which extra conditions on the integrity distribution maybe allows you to obtain a better result. For example, we had this example of the outstanding maximum degree, right? And I think that some case that is very interesting is the case where the degree is a power law distribution with index kappa. So for example, here, Sai did some simulations where you take the integrity to power law with index kappa, and the out degree, I'm always going to take it to be equal to 2. And then, so we're interested in this blue line. This blue line is just m pi max divided by delta minus. And our result says that this blue line should be above 1, right? So this tells you that it should be at least 1. But what you observe in the simulation is that it's not 1, that will be this line, but it's something that is somehow above 1, and converges to some constant. So I wouldn't say it's a conjecture, but our guess is that if you look for this interesting case of the power law distribution, then this pi max is going to be a constant factor off from this maximum in degree, where this constant factor is different than 1. So it's really like, it will be really interesting to study what's going on. And another interesting question is, what about dropping some conditions? So we are always interested in having the more general set of sequences that we can understand. So condition 2 is really technical. It's really for technical reasons, I mean. So I guess that it could be dropped and the results wouldn't change too much. Condition 1 is needed for this thing of having the random walk, of not having not like, if you don't have this condition 1, then you may have trivial stationary distributions. But in the case of PageRank, this is not true, because in the case of PageRank is immediate, that your pi is unique and is well defined and is supported on the whole graph, right? Because you can always jump from any vertex to any vertex. So it would be interesting to see which is the effect of having out degree 0 or 1 in the case of PageRank. And finally, the last problem that I would like to show you is what happens in general for the upper tail of this stationary distribution. So we have a good understanding when the in-degrees are power law distributed, then this tail is also power law distributed. And we know that when it's not power law distributed, then it's at most the bound that you get for the power law. So power law is maximizing the upper tail. But the upper bounds that we have, they are really not tight, and it would be interesting to understand exactly what's the behavior of this upper tail. So I'll stop here, and yeah, thanks for your attention.
Hey, Guillem, thank you for a lovely talk. There's an enormous amount there. So let me invite people to ask questions. You can ask in the chat, or you can just jump in and ask things. Maybe actually I could start by saying, how much do you think the conditions could be relaxed? So you talk about dropping the second condition.
Yeah. So I think, so as I say, like, I think that the condition 2, it's just a matter of understanding the technical problems that come. But I think that probably can be relaxed to having just, say, also a 2 plus epsilon bounded moment, or second, or say finite variance or something like this. I mean, I think that the results are still true if you allow the maximum, like the out degree, to behave like, or to put the same restriction for the out degree as you put for the in degree. It's also very interesting to think about what happens if your in degree distribution has infinite variance. So in this case, the random graph look very different. So it's like, so when you have, like, for example, finite mean but infinite variance, then you have this random graph that has log diameter. So they become much more small wall, and then things change a lot. So then I really think that condition 3 is needed for the sort of results that we're giving. And if condition 3 is not satisfied, then the results are going to change a lot. But it would be really interesting to understand how this affects the results.
Okay, and one other slightly vague question. So for the in A here, you've got this sort of log n factor.
Yeah.
So if you think about the random digraph that you get, are there sort of structural features that you can point at that kind of push you towards being at one end or the other?
I see. So for example, something I didn't say, but maybe it's also not difficult to prove, is that if your graph, for example, is Eulerian, then your pi of b is just d minus or d plus, because it's the same, because it's your Eulerian divided by m. So for example, in this case, it really pushes you to the left hand side if you have an Eulerian digraph. On the right hand side, the examples that we know on the right hand side are really because of kind of a typical I don't have a good answer for this, but really, like, my feeling really is that the upper bound is only going to be tight for small in degrees. So at the moment the in degree is large, I really think that you're going to be much closer to the lower bound than to the upper bound. So the upper bound is, this log n is somehow an artifact from the fluctuations that you have when you have your maximum in degree being constant. So when your maximum degree is being constant, then not all the neighborhoods behave typically. So they have these neighborhoods that behave kind of atypically. They kind of expand really well. And this is what creates this log n. But this is not something that's going to happen if your delta minus goes to infinity. So I really think that this log n shouldn't be there if you allow your in degree to grow at least logarithmic or something like this. Okay. I don't know if I gave you the answer.
That makes sense. Actually, one other question. What if you take a third level of randomness and take a random sequence? So take your degrees IID and something with.
I mean, definitely this can be used to study random Erdős-Rényi directed graphs where your degree sequence is random. And then essentially, like, if you know that with high probability your degree sequence is going to behave in a particular, for example, if you say, well, I generate this this random degree sequence, but I know that because the way I'm generating it, my maximum degree is going to be of order something. Then you can just kind of use the machinery that we have to say then, okay, then with high probability your maximum of the stationary distribution will be whatever. So I guess that you can also prove these kind of results.
Okay, cool.
Maybe I can ask just a quick question. So in your PageRank walk, you said that the lambda measure needed to be sort of sufficiently close to uniform. I imagine that's quite a technical condition, but can you give us an idea of how much space there is?
Yeah, so at the moment, so what our condition is something like lambda of b should be between n to the -1 plus epsilon and n to -1 minus epsilon. So you can allow for subpolynomial deviations. The problem otherwise is that if you put this teleportation probability that is very likely to go to a particular vertex, suddenly you are really changing the popularity of this vertex. And then pi max could change a lot. So I don't think, maybe the results are not even true if you have something that is, so if you have this teleporting distribution that really favors a particular set of vertices for some reason, then probably this set of vertices, maybe they can take the role of the pi max, and they can change a lot also the tail of the upper tail of the distribution for the stationary. So probably the parallel hypothesis in this case is not even true, because the teleporting distribution somehow has a too large impact.
I guess in some sense you want the lambda to be ignoring the geometry anyway. That's kind of its purpose.
Yeah, it's true. Yeah, no, I think there's a lot of, in fact, we didn't, I mean, we got this PageRank result, but somehow the PageRank result was, I mean, it was not a direct corollary, but it was coming from our results on random walks. But there's a huge literature on PageRank, and then you can you have all these parameters that you can tune. So maybe your alpha depends on the vertex that you are, maybe your lambda also depends on the vertex that you are, or I mean, not only the target vertex, but also the vertex that you're jumping from. So it's it's really like, and then there's really nice results in this respect. And so I don't know. So yeah, I'm sure there's lots of things to look at, and a lot of open questions in these open problems in this area.
Thanks.